In this video, I'd like to look at some little bit of data for Ohm's law. I want to look at specifically setting the intercept in a graph, in a trend line or a fit, doing what Excel calls forecasting to extend the fit line sort of beyond the data, and also a little bit on sort of interpreting these results. Okay, so I have some data that I have over here in a Word document. Copy it and paste it over here into Excel. Okay, and just the voltage was varied and then the current was measured. So when there was one thing that you sort of input and put in what you wanted to do, we usually put that on, by convention, the x-axis. And one thing we'll have to look into is one, these numbers are sort of right justified, so we clearly recognize them as a number. This number is centered. I think it's just some formatting it picked up from Word. And here's a hint that it understands it as a number, even though it's centered, is that it got rid of the point zeros. So it wouldn't do that if it were text. It wouldn't change your text. So it must be recognizing it as a number, but that is something you do need to watch out for. When I highlight the data and make the graph, I might include row 2, but I won't include row 1. That sort of that merged cell would probably really throw off Excel, or even just multiple headers would probably throw off Excel. So I don't want to confuse Excel. So maybe I should just highlight the numbers. I'm probably okay with the headers in row 2. So I can get rid of the Word document for now. Sorry. Damn it. All right. Sorry about that. So highlighting data, insert XY scatter. Here's the graph. Make sure the graph is highlighted. Chart design, quick layout number 9. And I don't want the label. Delete. This, what was on the x-axis was in the first column, and that's the voltage, which came in volts. And the y-axis was current, and that came in milliamps. And this is, I'll just say resistor data, or I could say Ohm's law. Okay, it gave me a fit to a straight line, but I want to compare this to Ohm's law, and Ohm's law is voltage equals resistance times current, but there's no constant term in there. And so my fit from Excel gave me a small 0.018, gave me a constant term, and I want to get rid of the constant term. So I want to show in Excel how to do that. So the same way you would do if you were changing it to a square, or a polynomial fit or an exponential fit, you right click on the line and say format the trend line. We're not going to change the type, but we're going to change the intercept. So I'm going to click this set intercept and set it to 0. Now it changed the equation. It got rid of the constant term in the equation. And some people see set intercept as 0, and then they want to see it go through the 0. And that's not what set intercept means. That means take the constant term in the fit equation and set it to 0. So it's doing something to the fit equation, not something to what this fit line does. But if you want the fit line to go back and go through the origin, then you can do that with Excel, and that is this forecast. So you can forecast forward or backward. And so these, I'm not quite sure why it's calling it period, but there are I want to go, my first data is 1, and I want to go backward by 1 to get to 0. So I can put in a 1 under the backward and get it to go through the origin. So set intercept was changing the fit equations, changing something about the fit equation. But if you want to change the display of the fit equation, that's forecasting. And you could also, I could go up to, let's say I wanted to go up to 7, so I would go 2 forward. So I can go forward and backward in my forecast. Set intercept changes something about the fit equation. I have forecasting, which can make my line extend beyond my data. Okay. One other thing I want to show is sort of in interpreting this equation here and comparing it to theory. So I'm going to, I want to sort of write, so I'm just going to do a little snipping here. So I have, this is just in lieu of a whiteboard. So I have, from Excel, I have this equation y equals 0.3011x. And then I look at my y-axis as current. So I'm going to make the y and I, and on the x-axis, I have voltage. So I'm going to make the x of V. But if I'm thinking of the theory is Ohm's law. And Ohm's law is usually given as V equals I times R. So what Excel gave us was solve for current, because we followed the convention of putting the thing we control, voltage, on the x-axis. So Excel gave us something solved for current, and the normal theory is solved for V. So let's solve this for V, solve what Excel gave us for V by dividing both sides by this 0.301. So that will cancel over here, and we'll have V equals, and I'm going to write it in this form, 1 divided by 0.3011 times I. That's the same as the line above. And now I can compare that to my theory of IR. And now I have a simple comparison. V is V, I is obviously I, and so then R is this 1.3011. So that, not the slope, but the inverse or the reciprocal of the slope is the resistance. A normal slope, my 0.301, my normal slope has units of y units over x units, milliamps over amps. So if I were to take the reciprocal to get the resistance, I would have reciprocal units. So let me use Excel here for a minute to equal 1 divided by 0.3011. Okay, so there is, this is 3.32, I'll say, and then the units are the reciprocal of the slope. So that would be volts over milliamps. And that happens to be kilo-ohms. So I have volts over amps is an ohm, and I have milli, which is small, 1,000th, in the denominator. So if I divide by something small, I'm going to get something big. So if I divide by thousandths, I get thousands, which is kilo. Okay, I think that's all I wanted to show you in this example. Thanks much for your attention.